Last episode ended on a punchline. Line integrals can depend on the entire path between two endpoints, not just on the endpoints themselves. We saw the rotational field around the unit circle give 2 pi, and the radial field around the same loop give 0. Today we isolate the well-behaved minority, the fields for which path does not matter. The slogan is this: a vector field f is conservative if it equals the gradient of some scalar function f, and for such fields the line integral collapses to f evaluated at the endpoint minus f evaluated at the starting point. That is the fundamental theorem of line integrals, and it is the direct multivariable analog of the fundamental theorem of calculus. By the end of this episode, you will have 3 equivalent characterizations of conservative fields: a clean two-dimensional test by mixed partial derivatives, a recipe for reconstructing the potential when the test passes, and 3 worked examples that pin down what is and is not allowed. The physical reading, conservative force fields like gravity admit a potential energy, non-conservative ones like friction do not, will make the whole construction feel inevitable. Here is the definition. A vector field f on an open set D in n-dimensional space is called conservative if there exists a scalar function f on D such that f equals the gradient of f at every point of D. The scalar f is called a potential function for f. The conservativeness is a property of f. The function f is the witness. In 2 dimensions, with f the vector pq, the condition becomes a pair of partial differential equations: the partial of f with respect to x equals p, and the partial of f with respect to y equals q. Find a single f satisfying both, and f is conservative. A note about physics conventions. Physicists usually call the negative of the potential energy u, so they write f equals negative the gradient of u. The minus sign comes from the convention that potential energy increases when you push a particle against the field. It is purely a sign convention. The mathematical content is identical to ours. We will stick with f equals the gradient of f. Here is the main theorem. Let f be a continuously differentiable scalar function on an open set D, and let C be a smooth-oriented curve in D from a point A to a point B. Then, the line integral of the gradient of f along C equals f at the endpoint minus f at the starting point. Look at what this says. The integrand is a vector field, the gradient of f. The integral could a priori depend on every detail of the curve, but the answer is just 2 numbers subtracted, the value of the potential at the end minus the value at the start. In 1 dimension, this is exactly the fundamental theorem of calculus. The gradient reduces to the ordinary derivative, dr reduces to dx, and the formula becomes the integral from a to b of f prime of x dx equals f of b minus f of a, verbatim, the fundamental theorem of calculus. So the fundamental theorem of line integrals is the natural multivariable upgrade, and it has the same content. Integration recovers a potential from its derivative up to the boundary values. The single most useful consequence, for a gradient field, the line integral depends only on the endpoints, not on the path. Why is the theorem true? 2 ingredients, both already in your hands. Ingredient 1, the multivariable chain rule. Define a one-variable function, g of t equals f of r of t, the value of the potential at the point on the curve corresponding to parameter t. The chain rule says g prime of t equals the gradient of f, evaluated at r of t, dotted with r prime of t. That is exactly the integrand of the line integral. Ingredient 2, the single variable fundamental theorem of calculus. Plug g prime into the definition of the line integral, and the integral becomes the integral from a to b of g prime of t dt, which by the fundamental theorem of calculus equals g of b minus g of a, which equals f of b minus f of a. Done. The whole proof is 2 lines. Chain rule turns the integrand into a total derivative along the parameter. Then the fundamental theorem of calculus integrates the total derivative. The structural content of the fundamental theorem of line integrals is exactly that, integration of a gradient telescopes, because the gradient is the directional derivative along the curve, and the directional derivative along the curve is a total derivative in the parameter. Beautiful, and the reason the theorem is called fundamental. Here is the structural backbone. 3 conditions on a continuous vector field, f on a connected open set, all equivalent. Condition 1, conservative, f equals the gradient of f for some scalar potential defined on the whole set. Condition 2, path-independent. The line integral of f from a to b gives the same answer for every smooth curve from a to b. Condition 3, zero circulation. The integral around every piecewise smooth closed loop is 0. The implications. 1 implies 2 is just the fundamental theorem of line integrals. If the field is a gradient, the integral collapses to f of b minus f of a, independent of path. 2 and 3 are equivalent because any closed loop can be split into two paths from A to B, one forward, one reversed, and equality of the two forward integrals is exactly the loop integral being 0. The harder direction is 2 implies 1, given path independence, you construct a potential by picking a base point x0 and defining f of x to be the line integral from x0 to x along any path. Path independence is exactly what makes this definition unambiguous, and a short argument with the limit definition of partial derivatives shows the gradient of f equals f. So the three conditions are a single phenomenon viewed from three angles. Here is the picture you should carry in your head. The blue arrows are a conservative vector field. A sample of f equals the gradient of f on a grid. The two thick curves are two completely different paths from the same starting point. A in the lower left to the same ending point, B in the upper right, the red curve, C1 arcs up and over the top, while the orange curve C2 takes the broken right, then up path. Visually, nothing about the two curves is the same. They sample the field at totally different points with totally different tangent directions. And yet the line integrals are equal. The line integral over C1 of f dot dr equals the line integral over C2 of f dot dr equals f of b minus f of a. The details of how you travel from A to B do not matter, only the endpoint values of the potential do. This is what conservativeness buys you, and it is the visual content of the fundamental theorem of line integrals. Now, a deeply practical question. Given a vector field f the vector pq, how do we decide whether it is conservative without counting for a potential? The answer in 2 dimensions is a single equation. On a simply connected domain, f is conservative if and only if the partial derivative of p with respect to y equals the partial derivative of q with respect to x. That is the mixed partials test. The three-dimensional analog is that the curl of f, a triple of differences of mixed partials, has to vanish. We will meet the curl explicitly when we do Stokes' theorem. For now, in 2 dimensions, one scalar equation decides everything. The necessity, if f equals the gradient of f, then p sub y equals q sub x, is purely Clairaut's theorem on equality of mixed partials. The sufficiency, if p sub y equals q sub x, then a potential exists, is the deeper half, and it is exactly where the topological hypothesis simply connected enters. The next 2 slides unpack both halves. Necessity is one line. If f is conservative, then p equals f sub x and q equals f sub y for some potential f. Differentiate p with respect to y and you get f sub xy. Differentiate q with respect to x and you get f sub yx. Clairaut's theorem from episode 4, continuously differentiable functions have equal mixed partials, gives f sub xy equals f sub y equals f sub y equals q sub x. Done. Any conservative field automatically passes the test. Sufficiency is harder, and it is where the topology matters. On a simply connected domain, a domain where every closed loop can be continuously shrunk to a point, no holes. The converse holds, p sub y equals q sub x implies a potential exists, and you build it by integrating f along an arbitrary path from a base point. The mixed partial equality is exactly what makes the path integral construction well defined, by an argument we will see in pristine form next episode when we prove Green's theorem. On domains with holes, think of the plane minus the origin, the test can pass locally everywhere while a global potential still fails to exist, because the loop around the missing point detects the hole. A short detour into the fine print, because it matters for physics. Simply connected means path connected, with the extra condition that every closed loop in the domain can be continuously shrunk to a point without leaving the domain. Informally, no holes. The whole plane is simply connected. A disk is simply connected. A plane with one point removed is not. Here is the classic counterexample to the test on a non-simply connected domain. Take D to be the plane with the origin removed, and consider f the vector negative y over x squared plus y squared and x over x squared plus y squared. A direct computation shows the partial of p with respect to y equals the partial of q with respect to x everywhere on D. So locally, near any point, this field has a potential. It is the angle function, arctangent of y over x, suitably interpreted. But integrate f around the unit circle and you get 2 pi, not 0. So globally, on this domain, f is not conservative. The angle is multi-valued. It changes by 2 pi every time you go around the origin. The hole at the origin is the topological obstruction. This is exactly the situation behind magnetic flux and Aharonov-Bohm in physics, and it is the reason the test needs simple connectedness to be an if and only if. Here is the recipe for actually constructing a potential. Once the test, p sub y equals q sub x, has confirmed one exists. Step 1. Integrate p with respect to x, treating y as a constant. This gives a candidate function of x and y, but with an unknown constant of integration that, in this multivariable setting, is a function of y alone. Call it g of y. So f of xy equals an antiderivative of p and x plus g of y. Step 2. Take the partial derivative of this candidate with respect to y and force it to equal q. That gives one equation involving g' of y. If you did the bookkeeping correctly, and this works precisely because p sub y equals q sub x, the expression for g' of y will involve y alone, no x left over. That is the magic moment. It is the test paying its dividend. Step 3. Integrate g' of y in the usual one-variable way to get g of y, then assemble the final potential. Always verify at the end by computing the gradient of f and checking it equals f. The whole procedure is mechanical once you have done 2 or 3. First example, doing the whole procedure. The field is f the vector 2xy x squared, so p equals 2xy and q equals x squared. Step 1. Run the test. The partial of p with respect to y is 2x. The partial of q with respect to x is 2x. They agree everywhere on the plane, which is simply connected, so f is conservative. Step 2. Construct the potential. Integrate p equals 2xy with respect to x, treating y as a constant. That gives x squared y plus an unknown g of y. So our candidate is f of xy equals x squared y plus g of y. Differentiate in y, the partial of f with respect to y is x squared plus g' of y. Force this to equal q equals x squared. The x squared on both sides cancels, leaving g' of y equals 0, so g of y is a constant. Take it to be 0. The potential is f of xy equals x squared y. Final sanity check, compute the gradient. The partial of x squared y with respect to x is 2xy, that is p. The partial with respect to y is x squared, that is q, verified. So f equals the gradient of x squared y. Second example, payoff time. Compute the line integral over c of 2x y dx plus x squared dy, where c is any smooth curve from the origin to the point 1, 2. By the previous slide, the integrand is exactly f.dr for f equals the gradient of x squared y. So the field is conservative, the potential is f of xy equals x squared y, and the fundamental theorem of line integrals tells us the integral is f of 1, 2 minus f of 0, 0, which is 1 times 2 minus 0 equals 2. That is the entire computation, no parametrization, no substitution, no integration. 2 endpoint evaluations and a subtraction. And it works for any smooth curve from 0, 0 to 1, 2. The straight line, the broken right then up path, a sinusoidal arc, anything. This was exactly the challenge problem at the end of the previous episode, and now you see the lightning-fast solution. The mixed partials test recognizes conservativeness. The recipe constructs the potential. The fundamental theorem of line integrals evaluates the line integral in 2 pen strokes. This is the power of the theorem. Third example, a negative result. Take f, the vector negative y, x, the rotational field from last episode. Apply the test. The partial of p equals negative y with respect to y is negative 1. The partial of q equals x with respect to x is plus 1. Minus 1 does not equal plus 1. The test fails on every open set, as is not conservative on the plane, and no potential function for it exists. We already knew this from last episode. The line integral of this field around the unit circle was 2 pi, non-zero, so condition 3 of the equivalence theorem fails. Hence, so do the other 2 conditions. The mixed partials test catches the failure instantly, without any loop integral. This is the field that carries circulation, and next episode Green's theorem will give us a formula relating the loop integral of f around a closed curve to a double integral over the enclosed region of the vary quantity q sub x minus p sub y. For this field, q sub x minus p sub y equals 1 minus negative 1 equals 2. And you can already see how the answer 2 pi will fall out of 2 times the area of the unit disk, pi. The mixed partials test is not just a binary yes-no, it measures by how much the field fails to be conservative. The physics is too beautiful to skip. A force F is called conservative in the physical sense if it is the negative gradient of a scalar function u called the potential energy. Gravity near Earth's surface, f the vector 0, 0, negative mg, is the gradient of mgz up to a sign. The potential energy is u equals mgz, height times mgz. Newtonian gravity from a point mass is the gradient of negative gm m over r. The Coulomb force from a point charge is the gradient of kq over r. The Hooke's law spring force is the gradient of 1/2 kx squared. Conservative forces are the rule rather than the exception in fundamental physics. The work energy theorem says the work done by the net force equals the change in kinetic energy. For a conservative force, by the fundamental theorem of line integrals, the work is u of a minus u of b, the drop in potential energy. Equating gives conservation of total mechanical energy. Kinetic plus potential is constant along the trajectory. This is where the word conservative comes from. Friction is the counterexample. It always opposes motion, and the work it does is negative and proportional to the path length. Double the path, double the energy dissipated. No potential function can capture that, because path length is not a function of endpoints. Friction converts mechanical energy into heat. Energy is conserved overall, but not in a form the fundamental theorem of line integrals can express. A word on history. The vocabulary we have been using, potential, conservative, circulation, crystallized during the 19th century in the work of Green, Stokes, Kelvin, and others on heat, electricity, and fluid flow. By the time Maxwell wrote down his unified treatment of electromagnetism in 1865, conservative fields and their potentials were the bread and butter of mathematical physics. The electric potential phi in electrostatics is exactly a potential function in our sense. The field is E equals negative, the gradient of phi. The culminating structural theorem is the Helmholtz decomposition from 1858. It says that any sufficiently nice vector field on three-dimensional space can be split uniquely into two pieces: a gradient piece, which is conservative or irrotational, and a curl piece, which has no sources and is solenoidal. Today's theorem completely characterizes the first piece. The second piece will occupy the rest of the series through Green's theorem, Stokes' theorem, and the divergence theorem. The Helmholtz decomposition is the goal that gives the whole vector calculus subject its structural shape. Recap. A vector field f is conservative if there exists a scalar potential f with f equals the gradient of f. For such fields, the fundamental theorem of line integrals says the line integral over c of the gradient of f dot dr equals f of b minus f of a. The line integral depends only on the endpoints, not on the path. Three properties are equivalent on a connected open domain: conservative, path-independent, and zero around every closed loop. In two dimensions, on a simply connected domain, f the vector pq is conservative precisely when p sub y equals q sub x. When the test passes, build the potential by integrating p with respect to x, introducing an unknown g of y, differentiating in y, matching q, and solving for g prime of y. We worked f the vector 2xy, x squared, the test passes, the potential is x squared y, and the fundamental theorem of line integrals evaluates the line integral from 0, 0 to 1, 2 as 2 instantly. The rotational field, the vector negative yx, fails the test. Negative 1 does not equal 1, and is not conservative. Physically, gravity and electrostatics admit potential energies because they are conservative. Friction does not, because it depends on path length, not endpoints. That's conservative fields and the fundamental theorem of line integrals. A field is conservative when it is the gradient of a potential. For such fields, the line integral is just the difference of the potential at the endpoints, independent of the path. The test in two dimensions is equality of mixed partials. The recipe to build a potential is partial integration. If this helped, like, subscribe, and try today's challenge. Is f the vector e to the x sine y plus 3 and e to the x cosine y plus 2y conservative? If yes, find its potential and use the fundamental theorem of line integrals to evaluate the line integral from the origin to natural log of 2 pi. Hint, start by checking p sub y and q sub x, and if they match, integrate p and x to begin the potential. Next episode, Green's theorem. We turn the line integral around a closed loop in the plane into a double integral over the enclosed region, even when the field is not conservative. The mixed partial difference, q sub x minus p sub y, that we use today as a pass-fail test becomes the integrand of a beautiful conversion formula. See you there! A vector field f is conservative if f equals del f for some scalar potential f. For such fields, the fundamental theorem of line integrals states in Tc del f dot doctor equals f of b minus f of a, where b and a are the end and start of c. The integral depends only on the endpoints. Three properties are equivalent: f conservative in Tcf dot doctor path independent, oint cf dot doctor equals 0 on every loop. In two dimensions, on a simply connected domain, f equals the vector p, q is conservative if partial pb partial, y equals partial qp partial x, Clairaut. A potential is reconstructed by integrating p in x, introducing an unknown g of y, differentiating in y, and matching q. Worked examples: the vector 2xe, x squared, is conservative with f equals x squared e, so in t equals 2 from 0 thou to 1 2 regardless of path, the vector minus y, x fails the mixed. Physically, gravity is conservative, friction is not. Next episode, what happens when the field is not conservative around a closed loop? The answer is Green's theorem. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.